Little review of factorial notation. When simplifying with factorial notation without your calculator, expand the bigger number. In this case, 7 is bigger until you get to the smaller number, because then those will simplify, and the answer to A is 42. Which is our bigger number in B? Is 10. So expand 10 until you get to one of the factorials on the bottom. Those 6 factorials will cancel. 4 factorials, 4 times 3 times 2 times 1. If I was doing this mental math, can you see that 4 times 2 is 8? Those would simplify. Can you see that only thing I'm left with on the bottom is a 3? I like to color code this so you can see what I'm doing at the same time. What is 9 divided by 3? Just left with 3. Everything in my denominator has simplified away. I'm left with 10 times 3 times 7. That you can do with mental math. 21 times 10, 210. Okay, so I color-coded things so that you could see it better. First of all, I expanded the top, 10, 9, 8, 7, until I got to 6 factorial, so I could cancel that out with the 6 factorial on the bottom. I did that in red. I also had 4 factorial on the bottom, which I expanded to be 4 times 3 times 2 times 1. I know that 4 times 2 is 8, so in the green, I canceled the 8 in my numerator out with the 4 and the 2 in my denominator. That left only the 3 in my denominator left. I simplified the 9 and the 3 because 9 divided by 3 is 3 in purple, leaving 10, 7, and a 3 in my numerator. I multiplied those together to get 210. 8 canceled out with the 4 and the 2 on the bottom in green. The 3 was, well, when multiplying numbers, 4 times 3 times 2, I can choose whatever order I want. 4 times 2 is 8. That 8 could cancel out with the 8 in the numerator. And then once we get to variables in part C, which is bigger, n plus 2 or n? N plus 2. So we start expanding the bigger one, n plus 2. What would go next? 1 less would be n plus 1. What would go next? N. And once you get to n, since that's what's in your denominator, you can cancel those, simplify away, and we're just left with n plus 2 times n plus 1. So again, this is something that we've seen already working with factorial notation, which leads us into permutations, which is arranging objects in a specific order. And this is going to be a key word moving forward, because the second part of this unit is combinations where the order doesn't matter. So we start off with permutations where the orders matter. If you want to write all the permutations of ABC, first of all, 3 letters. We can figure out how many there's going to be. How many choices do you have for your first letter? 3, then 2, then 1. There should be 6. ABC, ACB, BAC, BCA, CAB, CBA. There are all 6. It's not very often that an exam question would get you to list something. Instead, they ask how many there would be. We've seen our formula, and this formula is on our formula sheet. In this case, when they ask for all the permutations, or when they give you a set of letters, it's like you have a physical A, a physical B, and a physical C. So you're not allowed to repeat. On my questions on the exam, I will try to be very specific, saying repetition is not allowed or repetition is allowed. So if you're allowed to use more than one A or more than one B. But in the case where it says permutations, a permutation is an arrangement of objects in a specific order, meaning that you are given those objects, you imagine them like a physical A, a physical B, a physical C, that you can rearrange, and you only have one of each. So we've seen our permutations formula. That's on our formula sheet. We have some special cases. NPN. Okay? If you had 5P5, well, that would be 5 spaces starting with 5, which would be 5 factorial. Notice that in this formula, when you have NPN, 0 factorial appears. And this is why we defined 0 factorial earlier to be 1, because this formula still needs to work in this situation. And so that's why 0 factorial is 1. What's that? They do. 0 factorial is 1. And then you just get n factorial as the answer. And we can see from the spaces it has to be 5 factorial. If you had 5 spaces starting with the number 5, you would get 5 factorial. The formula needs to show that as well. All right. So our wind ensemble has 10 pieces that are really, really good. Is this true? And they want to make a program where the order matters for a concert. Well, you could do this with spaces. We have 4 decisions. How many choices for the first song? 10, then 9, then 8, then 7. Chances are they're not going to play the same song 4 times in a row. This is the same as 10P4. Order matters because if one of them is O Canada, it's very atypical to play that one third. How many permutations are there of the word math? Well, you could do spaces, 4 choices, then 3, then 2, then 1. This is the same as 4 factorial, which is the same as 4P4. Yes? No. Permutation is only if you have no repetition, where you're arranging objects in an order. So example 4 is the first abstract one that comes up with permutations. You have to remember with the fundamental counting principle that you make spaces for the number of decisions that you need to make. And then you put your choices into those decisions. So what makes this question hard is because 5 people come for math help and there are 12 desks. You like to put students into desks. That's what happens. Very rarely do you put a desk into a student, unless the teacher is very angry. But that doesn't happen very often. And there's rules against those kind of things now. Anyways, so because of that, when drawing the spaces, the number one mistake in this one is to draw 12 spaces for 12 desks. But we have to remember that our spaces represent decisions. And how many decisions need to be made The first student comes in, needs to decide where to sit. The second student, the third student, the fourth student, the fifth student. There's going to be 5 decisions that need to be made. When the first student comes in, how many places can they sit? 12, because there's 12 desks available. Now, if you've ever come for math help when the second person comes in, it's awkward if that second person decides to sit on the lap of the first person, okay? So the number of decisions for the second person are 11. They will not sit in the same desk. They will choose another desk. And then 10, and then 9, and then 8, which is the same as 12p5. The p is supposed to be big. The other numbers are small, like that. That's to really exemplify. So if I was drawing this on a piece of paper, there's my line. It's a capital P. It's on the line, and the other numbers are subscript below. Should I write it like this so you really can see it? Yeah, I could even do it. Oh. That is a weird P. I don't like that P at all. Okay. Ugh. Let's get rid of it. Here we go. Good. 12p5. So then the question becomes, how many seating plans could we have in this class? 5, 10, 15, 20, 25, 30. There's 33 desks, and there's 24 of you. The number of seating plans would be 33p24. How big of a number is this? Clear O. I have to turn my calculator off because it's not responding. Very big. Do you have it on your calculator?
Yeah, 2.39.
Okay. I just want to give you an idea. I'll use all the numbers here that we have. Just want to give you an idea of how big this number is. All right. Now that's rounding, that's estimation, because there would actually be numbers there, but our calculator only has the first 8 or 9 digits, so those rest I'm just putting as zeros as placeholders. That's how big it is.
But isn't that obligation that like the entire seating plan needs to be the same except for one person moving?
1 person moving would be a new seating plan. So if you moved 1 desk back because it's empty, it would be considered a new seating plan. Okay? Which is crazy an amount. So if I could literally go, you know what? I've made a new seating plan. If anybody guesses it right, they get 100% in the course, and I'll give them $1 million. And every month we'll have the contest, right? Okay? Your chances are so close to 0 of getting it right, but it is possible. Okay? We could try it right now. Okay?